Hi everyone, my name is Ria and I was a summer intern at NICTA for 8 weeks. I am currently undertaking a Master of Science in Operations Research at Melbourne Uni. During my internship, I worked in the Optimisation Research Group with Dr. Andreas Schutt. My project involved investigating the performance of various optimisation solvers on scheduling problems, in particular the multi-mode resource-constrained project scheduling problem. In this presentation, I'll give a definition of MRC-PSP and then run through the model which was written in Minizinc. I'll summarise the results from the experiments before concluding with a reflection on my summer scholar experience. So what is the multi-mode resource-constrained project scheduling problem? To those of you who aren't too familiar with optimisation, the MRC-PSP can sound like a bit of a mouthful, and even after 8 weeks of this internship, I still sometimes struggle to get all those words out. The problem is NP-hard and has been solved using various exact and heuristic methods. I'll define it by breaking it into smaller pieces, namely the basic project scheduling problem, resource constraints, and multi-mode tasks. The fundamental part to the problem is the project scheduling. In this type of problem, we're given a set of tasks that need to be completed. This is represented in Minizinc as shown here, where n subtask is the number of tasks. Each task has an associated duration, as well as a set of predecessors, that is, a set of tasks that need to be completed before the task can start. In this problem, the decision is to choose the starting time for each task so that the total completion time of the project is minimal. In the resource constraint problem, we're given a set of resources, which uses a similar Minizinc representation as before. The resources can be divided into two types, renewable and non-renewable. Each resource has a specified capacity that cannot be exceeded, and each task has a specified amount required of each resource. New constraints need to be added to the project scheduling problem to ensure that the capacity limitations are met. Lastly, in the multi-mode problem, each task has a set of different modes in which it can be executed. We represent this by defining a new set of optional tasks corresponding to each of the different modes. We then specify the set of modes for each of the original tasks, as shown here. The difference now is that each mode has a different duration and different resource requirements, thus giving us the added decision of choosing which mode to execute each task in. To illustrate the problem, I'll show a sample data file. We are given the number of resources, in this case 4, with the corresponding types, where 1 means it is a renewable resource and 2 a non-renewable. The resource capacities are also given. For example, resource number 1, which is renewable, might be a bricklayer, and in this instance we are not allowed to be using any more than 11 bricklayers at any one time. Resource number 3, which is non-renewable, might be the number of bricks, and in this case we are limited to using at most 42 bricks over the course of the whole project. Well, these numbers probably aren't very realistic for that example, but you get the idea. We have a set of 5 tasks, each of which can be executed in one of 3 different modes. This equates to 15 optional tasks altogether. Finally, the predecessors, durations, and resource requirements of each task are given. For example, task 1 has modes 1, 2, and 3. It has no predecessors, so it can be started at any time, regardless of which tasks have already been completed. In mode 1, it has duration 1, mode 2, duration 4, and mode 3, duration 6. As for resource requirements, the first row corresponds to the consumption of resource number 1. That is, in mode 1, the task requires 7 units of resource 1, mode 2 requires 2 units, and mode 3 requires 0 units. Now that I've described the problem, I'll explain the model I used to solve it. Minizinc is a constraint programming language developed by NICTA, and having spent a whole semester learning it at uni, it was the obvious choice of modelling language. In any type of optimization problem, we start with the decision variables. That is, what are the things we need to decide on? In our problem, there are two main decision variables. Firstly, we want to decide what time to start each task. This is represented in Minizinc by a one-dimensional array with an integer value corresponding to each task's start time. Secondly, in the multi-mode problem, we need to decide which mode to execute each task in. I took two different approaches to model this. In my first model, I used an array of integer variables to represent the selected mode. Recall here that opt refers to the set of optional tasks. In the second model, I had an array of Boolean variables for each optional task, this time indicating whether or not that task was executed. Here is an example of a solution. In the first model, we have an array of size 5, showing that task 1 should be executed in mode 1, task 2 in mode 4, and so on. While in the second model, we have that optional task 1 is executed, optional task 2 is not, 3 is not, 4 is, and so on. The next step is to encode our constraints. For the next few slides, I will only show the code for the model with integer variables, as the code in the other model is fairly similar. So first we need to ensure that an allowed mode is chosen for each task, as shown by the constraint here. The value assigned as mode selected of each task is inside the set of modes of that task. We also need to ensure that the precedence constraints are met. In Minizinc, this is encoded by specifying that the start time of each task is greater than or equal to the end time of all of its predecessors, where end time is the start time plus duration, as seen here. Now for the resource constraints. We need a different type of constraint for the two types of resources. For non-renewable resources, we simply need a linear inequality that ensures that the total amount of resource consumed is not exceeded by the end of the project. Here, NR is the set of non-renewable resources, and we sum over all tasks to find the total amount consumed of that resource. The renewable resource constraint is a little trickier to encode, but fortunately Minizinc includes a library of what are called global constraints. These are predefined constraints which are used as a way of encapsulating a set of other constraints. Many solvers implement special inference algorithms which make solving more efficient. The one that is useful in this case is called the cumulative global constraint, which sums up the amount of resource being used at any one time. To visualize this, we can picture the resource consumption as blocks as shown here, where each different color is a different task. The horizontal axis represents the duration of the task, and the vertical axis represents the resource requirements of that task. In the first diagram, the resource capacity is exceeded, while in the second diagram, the resource capacity is satisfied by moving task 2 forward by 1 unit. Finally, we must define the objective of the model. In most scheduling problems, the objective is to minimize the total completion time of the project, also known as the makespan. We define a new variable and add a constraint that ensures it is greater than or equal to all of the end times. Now that the model has been defined, we use a solver to find the best solution that satisfies all the given constraints. In general, the way that Minizinc works is that it finds a solution and then continues to search for another solution with a smaller makespan. It will continue this procedure until it cannot find any better solutions. For large data instances, this search procedure can take a lot of time, so it can sometimes be useful to tell the solver how to search for solutions by defining search strategies. Here are two of the search strategies that I tested. The first one chooses a mode at random for each task, and then will set the start time to as small a value as possible. The second strategy starts at the smallest possible value of the makespan, and if a solution cannot be found with that makespan, it increments it by 1 unit and continues this process until a solution is found. After writing the model, the next step was to run experiments to test out different solvers and search strategies. The data instances were taken from an online library of data which has been used by many researchers. The optimal values to almost all instances are available on the website, so I was able to compare my solutions to these known values. All up, there are about 11,000 data instances sorted into 20 different benchmarks. Each benchmark had a specific characteristic, for example, the number of tasks or the number of resources. One particular benchmark that was of interest was the one with instances with 30 tasks. There are 552 of these instances, and to the best of our knowledge, only 506 of these have previously been solved to optimality, leaving 46 yet to be solved. From now on, I will refer to these hard instances as the J30 instances. I took a selection of very competitive solvers, including Chuffed and LazyFD, both developed by NICTA, as well as Opturian CPX, G-Code, and Mistral. I tested these on both versions of my model, as well as using different search strategies. In my experiments, the solver that performed the best was Chuffed. Using its default search on the integer variable model, we were able to obtain optimal solutions for all data instances, including those that had never been solved to optimality. The average solve time was under 1 second for all benchmarks, except for the hard J30 instances. And for these J30 instances, 91% of them were solved in under 10 seconds, and all but 8 instances were solved in under 10 minutes. This table summarises the results of the hard J30 instances when using the default search and a time limit of 10 minutes. As mentioned previously, Chuffed was able to solve all but 8 instances to optimality within the time limit, with the other solvers finding fewer optimal solutions. For all benchmarks excluding the J30s, both Chuffed and LazyFD were the only solvers that were able to solve all instances to optimality. To give you an idea of how the different solvers performed on these instances, here are the results from the J14 instances using each solver's default search. In this graph, blue represents the proportion of instances solved to optimality, orange represents the proportion for which solutions were found but were not necessarily the best solutions, and the grey is for the proportion for which no solutions were found at all. As you can see, both Chuffed and LazyFD have 100% optimal solutions, and CPX has a tiny proportion of suboptimal solutions. G-Code and Mistral did not perform as well, both having greater proportions of suboptimal and no solution instances. Similarly, when the number of tasks is increased to 20 in the J20 benchmarks, Chuffed and LazyFD can solve all instances to optimality, while the other 3 solvers found even fewer optimal solutions. To illustrate the performance of the different search strategies, this graph shows the results from the J30 instances using the solver G12 LazyFD. In this case, giving the solver more information about the structure of the problem, as is done when using the mode then start strategy on the right-hand side, does not improve the quality of solutions found, meaning that LazyFD's default search is already strong. In general, the default search of other solvers also performed better than this user-defined search strategy. There is much potential for further research on this project. Pre-processing of the data to determine whether any solutions can be eliminated before solving with Minizinc could speed up computation time. Improvements to the model, such as extra constraints and other search strategies, could also have an impact on the solve time as well as increase the number of instances solving to optimality. My internship at NICTA was a great experience. Coming from a maths background, I hadn't had a whole lot of experience with bash scripting at all, so I learnt that a large portion of a computer scientist's time is spent debugging, and while I achieved nice results in the end, it took a fair few improvements to my model to get all the instances solving to optimality. Nonetheless, the learning process along the way was invaluable. Finally, I would like to say a big thank you to my supervisor Andreas, without whom I would not have accomplished anything in my project. His guidance and patience throughout my internship is very much appreciated. Also, to everyone else I met at NICTA, thank you for making my internship a truly enjoyable experience.